The main objective is to show an actual engineering prototype of a 7 nanometer ASIC artificial intelligence neural cognitive system on chip SoC design. Topics covered include designing and building the artificial intelligence CPU, the ASIC verification process and methodology applied in this design, and finally, the implementation of the artificial intelligent CPU in the actual demonstration of the autonomous vehicle controller system, which will illustrate a system design based on an autonomous vehicle application. The 7 nanometer ASIC technology node is the successor to the 10 nanometer node. The basis for sub-20 nanometer fabrication is the FET, field effect transistor. 7 nanometer resolution is difficult to achieve in a polymetric resist, even with electron beam lithography. In addition, the chemical effect of ionizing radiation also limit reliable resolution to about 30 nanometers, which is also achievable using current state-of-the-art immersion lithography. Hard mask materials and multiple patterns are required. Our ASIC neural artificial intelligence CPU 10 nanometer technology uses extreme ultraviolet lithography, EUV lithography, capable of resolving features below 20 nanometers in conventional lithography style. The 3D effective nature of the EUV masks result in new anomalies in the imaging. One particular nuisance is the two-bar effect, where a pair of identical bar-shaped features do not focus identically. One feature is essentially in the shadow of the other. The two features generally have different CDs, which change through focus, and these features also shift position through focus. Application-specific integrated circuit device or based on an FPGA application. Also, an important segment of the CPU infrastructure is the control unit. The control unit follows the stored list of instructions directing the activities of the arithmetic unit, the I/O devices, until the program has run to completion. Each unit performs its task under the synchronizing influence of the control unit. An important segment of the CPU architecture is the arithmetic logic unit, which are combinational or sequential logic circuits to perform operations on data as instructed by the control unit. Each arithmetic logic unit is characterized by the type of data that it can manipulate and the test of operations that it can perform on the data. The ALU supports operations on integers of different sizes and may also include operations to manipulate the fixed point and floating point numbers and various numeric data. Such specifications are part of the arithmetic add, subtract, multiply, divide, logical and or an exclusive, shift and rotate data, convert data from one type to another. In this design, the memory hierarchy is well defined. The high speed of hits and misses is important. For instance, hit time is the time to access the upper level of memory hierarchy, which includes the time to determine whether the access is a hit or a miss. Miss penalty is the time to replace a block in the upper level with the corresponding block from the lower level, plus the time to deliver this block to the requesting device, normally the CPU. The miss penalty is further divided into two components: access time, the time to access the first word of a block on a miss, and transfer time, the additional time to transfer the remaining words in the block. Access time is related to the latency of the lower level memory, while transferring time is related to the bandwidth between the lower level and upper level memories. Sometimes access latency is used to mean access time. The memory address is divided into pieces that access each part of the hierarchy. The block frame address is the higher order of the address that identifies a block at the level of the hierarchy. CPU clock cycles to recover from an I/O activity, such as cache flush, list the memory and I/O bus resource demands of each I/O device, even when the CPU is not using memory. The bandwidth of main memory and the I/O bus are limited. The final step is establishing performance of the different ways to organize these I/O devices. Performance can only be properly evaluated with simulation, though it may be estimated using queuing theory. Defining the processor data path. It consists of execution units such as arithmetic logic unit and shifters, the registers, the communication paths between them. The data path contains most of the state of the processor, the information that must be saved for a program to be suspended and then restored for execution to continue. In addition to the user-visible general-purpose registers, the state includes the program counter, the interrupt address register, and the program status register. The latter contains all the status flags for the machine, for the CPU, such as interrupts enable, condition codes, etc. In designing an I/O system, analyze performance, cost, and capacity using varying I/O connection schemes and different numbers of I/O devices of each type. Follow the design of an I/O system. List the different types of I/O devices to be connected to the machine and list the standard buses that the CPU will support. 2. List the physical requirements for each I/O device. This includes volume, power, connectors, bus slots, and expansion. 3. List the cost of each I/O device, including the portion of cost of any controller needed for the CPU. Record the CPU resource demands of each I/O device. It will include clock cycles for instruction used to initiate an I/O, to support operation of an I/O device, such as handling interrupts and complete I/O. CPU clock stalls due to waiting for I/O to finish using the memory, bus, or cache. CPU clock cycles to recover from an I/O activity. The range of caches from direct mapped to fully associative is really a continuum of levels of set associativity. Direct map is simply one-way set associative, and a fully associative cache with M blocks could be called M-way set associative. Cache represents the level of memory hierarchy between the CPU and main memory. In general terms, a well-defined cache will have the following parameters: the block line size, the hit time, the miss penalty, access time, transfer time, miss rate, and cache size. The CPU design at its core uses a well-balanced pipeline coupled with excellent partitioning and mechanisms that compensate for increased pipeline latencies. This enables the use of simple and well-structured logic functions within each pipeline stage to achieve optimal synthesis. The synthesis-based ASIC design flow and methodology are illustrated in this video. The ASIC design flow using synthesis follows these procedures. The functional specification of the design is done. The HDL coding and VHDL in Verilog RTL. The RTL behavioral or functional simulation of the VHDL code. The logic synthesis, followed by test, insertion, and ATPG. Then the post-synthesis or gate level simulation, and finally floor planning and place and route. The synthesis process was divided into two segments. The first segment employed a bottoms-up approach using design compiler in which all top-level blocks were synthesized using estimated constraints. Also, the layout process was completed. Here, the gate-level netlist is converted to a complete physical geometric representation. The first step was to do floor planning, which is the process of placing the various blocks and the I/O pads across the chip area based on the design constraints. Then placement of physical elements within each block and integration of all analog blocks or the external intellectual property cores is performed. When all elements are placed, a global and detailed routing is running to connect all the elements together. Also, after this phase, a complete simulation was done to ensure the layout phase was properly completed. Finally, the file produced at the output of the layout is the GDS2 file, which is the file used by the foundry to fabricate the silicon. The layout should be done according to Silicon Foundry design rules. ASIC system-on-chip design methodology. Emphasis on functional verification. Functional verification is part of the ASIC design methodology in order to ensure that your design meets functional requirements. Verification process provides for gate-level event simulation, gate-level cycle simulation, gate-level hardware acceleration, and Boolean equivalency checking. Keeping complex verification environments tractable means increasing the level of abstraction with transaction accuracy. The verification model consists of sequencer, transactions, and drivers. Virtual sequencer, verification components, device under test, DUT, verification components, scoreboard. Methodology integrates a build phase, a connect phase, end of elaboration, start of simulation, run phase, extract, check, report, and final phase. That is part of the verification methodology. On this software verification model, interface design under test, we use the interface to drive the clock driven directly from the top level. The virtual interface comes into play, and the virtual interface comes to a pointer and puts it into the UVM and fixed database. Constrained random verification consists and integrates checkers, coverage, and constraints. There are several phases that makes up the transaction level communication, message, reporting, end of test, and register layer. It can later retrieve other UVM clocks, and then you can start and run the test as shown in this display. Under the engine, build phase, connect phase, and run phase. Gate level simulation methodology, the Verilog simulation with back annotated delays, VHDL simulation, vital, compliant VHDL models, and back annotated delays. Verification tools supported are Avanti, Polaris, Cadence Verilog XL, Leapfrog, ICOS, Mentor Graphics Model Simulation, QuickTurn, and Synopsys VCS, as well as Vera. Functional verification for the MAC core is performed with an automatic stimulus generation and randomized testing. Stimulus generation for the Mac controller, the test is divided into three categories: normal, transmit, receive with errors. An important element of the Mac verification process is controlling packet distribution, packet size, the Mac destination address, alignment of errors, and CRC error packets. The network events includes collision. The Mac test bench sends packets in full duplex mode, produces random number generator functions, provides polymorphism, support cycle accurate reference models, and also semaphore registers. There are two main types of formal verification, that is model checking and equivalency checking. In model checking, the verification engineer writes invariants for the DUT, design under test. ASIC design methodology consists of VHDL design entry, functional simulation, logic synthesis, timing analysis, IDIF, gate level simulation, test vector generation, and fault simulation. The design entry in Verilog HDL or VHDL describe the identity declaration, the architecture body, the configuration declaration, package declaration, and package body. Functional simulation with vital sign-off simulation and model sim. Chip synthesis allows for translation optimization, and mapping of your ASIC design. The translation reads and analyzes and elaborates. Optimization to constrain the design, and mapping design database and design IDIF. Analyze performs syntax HDL checking and synapses rule checking. It stores intermediate files in your design library, .sim, .sin, .mra file, each HDL design unit. Need to partition the design for synthesis, separate distinct functions. Implement the design where soft macros such as adders, comparators, etc. System level verification. ASIC SoC methodology. Verification models consists of RTL, memory blocks, and software macros. The physical environment contains the hard macros and hardware test benches. For in-circuit verification, the target system, software environment, debugger, and CVE are supported. Test benches include the Model SIM, VCS, Verilog XL, and the stimulus consists of synthesizable test bench and test vectors. Machine learning and artificial intelligence application. The FIFO ASIC design methodology test bench consists of the test flow, the FIFO device under test, DUT, the read interface, and the coverage monitor. FIFO generator. The FIFO generator core generates fully verified first in, first out FIFO memory queues. The FIFO core provides an optimized solution for all FIFO configurations and delivers 500 MHz performance. It supports FIFO data bits from 1 to 1024 bits, supports independent clock domains. Our sophisticated FIFOs also support error correction, support for packet mode, and supports asymmetric ratios, read-to-write port ratios. FIFO process with randomization coverage. Component declaration. The number of coverage beans. Setting the bus for FIFO. Sending the number of words to the FIFO. Writing to the FIFO. Initializing the generator. Count FIFO transitions. ASIC System on Chip Design Methodology. Autonomous rover and vehicle systems. Preparing for the next frontier when thought, control, and thinking machines seamlessly brain-computer interfaces using fusion sensors to control autonomous vehicles as it relates to neuromorphic artificial intelligence platforms. The sensor fusion subsystem state model is based on abstract mathematical concepts including position and orientation in three-dimensional space. The state consists of three components: position, orientation, and velocity. geometric intuitive correction algorithms, and the support of quaternion Kalman mathematical filters form part of the artificial intelligence autonomous reference platform. Artificial intelligence methodology applied in this autonomous vehicle prototype. Machine learning, a subset of artificial intelligence, trains the autonomous vehicle how to learn. Machine learning mathematical models look for pattern in data. The scope of this framework is to present and to illustrate a realistic artificial intelligence autonomous vehicle engineering prototype. Pattern matching, image recognition, and object tracking form part of the artificial intelligence video system. Image recognition, as it relates to machine vision, is the ability of software algorithms to identify objects, places, people, writing, and actions in images. Convolutional neural network takes advantage of the fact that in any given image, proximity is strongly correlated with similarity. That is, two pixels that are near one another in a given image are more likely to be related than two pixels that are further apart. In a typical neural network, every pixel gets connected to every single neuron. In this case, the added computational load actually makes the network less rather than more accurate. Image recognition convolutional neural network algorithms can function by use of comparative 3D models, appearances from different angles, using edge detection. Image recognition algorithms are often trained on millions of pre-labeled pictures with guided system learning. The result is a pooling array containing only those parts of the image that are more important while discarding the rest, which both minimizes the computations that are needed to do while also avoiding the problem of overfitting. This prototype presents the design and implementation of an autonomous driverless vehicle. The system explicitly maps the static obstacles, detects and tracks moving obstacles. The intelligent vehicle integrates GNSS technology and external sensors data. Provides a 360-degree high-resolution mapping with short to long range measurement distance. It is integrated by an optical front end, a signal conditioning, object identification, object classification, and algorithm-based decision making, an analog to digital conversion, a control and synchronization with external light source. Signal processing is provided for distance output. The light detection and ranging system is an active form of remote sensing, measuring distance to targets, surfaces, using narrow beams of near-infrared light. The system scans the speed of vehicles ahead and the orientation sensors, tracks motion and balance.